Hello everyone, this is a video about electrocyclic reactions. These are a particular class of pericyclic reactions in organic chemistry, and they can be described using the Woodward-Hoffmann rules. I want to run through lots of different ways that you can analyze a system like this using the Woodward-Hoffmann rules, and also go on to show how you can use this type of chemistry and analysis in natural product retrosynthesis. This is a complementary video to another one I've made on pericyclic reactions, specifically on Cycloadditions, and you can find a link in the description below. If you find the video helpful, please do give it a like and share and subscribe to my channel. Okay, the first job that we have to do when we're looking at pericyclic reactions is to check that we're in the right class. An electrocyclic reaction is one where you have one whole pi system. I'm just going to represent it with this curve here, and these blue blobs at the end are just going to be the end atoms. So this is a pi system. And during the course of the reaction, the electrons whiz around and we form a new sigma bond between the two carbons at the end of the previous pi system, and we form a ring where we've shortened the overall pi system that's left. So the hallmarks of this type of reaction, when we form a ring, are that we form one new sigma bond, and we also shorten the pi system. So an important consequence of that is that often the delta H for this ring closing process is negative, as the sigma bonds in the product are usually stronger than the pi bonds that are being lost in the starting material. Now, one thing that will turn out to be important when using the Woodward-Hoffmann rules is to actually identify that this reaction is not normally a one-way process. This reaction is potentially reversible given the system, and we can use that to help our Woodward-Hoffmann analysis. We can also use that to help plan out syntheses, as it allows alternative routes for the reaction to all be explored, and we can put the reaction under thermodynamic control overall. Okay, so just some examples. So a classic example of an electrocyclic ring closure would be using this triene. When we treat this with heat or UV light, just using Hν there to represent the photochemical transformation, the electrons can whiz around in a ring to form our new sigma bond over here on the right-hand side in purple, our shortened pi system here on the left. So overall, we've lost a carbon-carbon pi bond and some delocalization energy at the expense of forming a really strong sigma bond. This pushes the position of equilibrium towards the right-hand side. So you have to watch out for these in syntheses. If you happen to make pi systems, accidentally heating them up too much can cause them to cyclize into something you may or may not want. The position of equilibrium goes the other way when we consider this butadiene. The cyclization to form this four-membered ring is not so favorable because we gain a lot of strain in those bonds. So for example, the new carbon-carbon sigma bond enthalpy is nowhere near as big as it was before. There's actually a preference for the reaction to go backwards when we treat it with the usual conditions of heat or light. And just another example of where we might use this to make a more complex looking molecule. If I made this tosylated ochem, note that this CN double bond has probably come from a carbonyl. We can use an electrocyclic reaction to form a heterocycle. When we treat this system with heat, we'll form a new carbon-nitrogen sigma bond and a ring. The double bonds are now in new positions. Still have a tosylate on that nitrogen, and R1 and R2 are still here. And now we have a system that's just one elimination away from forming an aromatic system, which would be very thermodynamically favorable. So if we have something in the reaction, say a base, to take that proton at this stage, we can eliminate tosic acid and form the pyridine ring. So the driving force for this process is forming aromaticity. Now, there's just a word of warning if you're planning these into your retrosyntheses. Just in the starting material, this double bond highlighted in yellow, this must be in the Z geometry. And this is purely to get the two ends of the pi system next to each other so that they can actually reach and do the electrocyclisation. Now, interestingly, you can form defined stereochemistry using these types of reactions. So the big question when using the Woodward-Hoffmann rules is this ring closure disrotatory or conrotatory? That means when the new sigma bond forms, do all of the other atoms all rotate in the same sense, say both clockwise or both anti-clockwise? That would be conrotatory. Or do they rotate in opposite directions, which would be called disrotatory? This will set up stereocenters in the products if there are substituents on those end carbons. Now that's best seen seeing an example. So to use the Woodward-Hoffmann rules, I need to define some conditions first. So I'm going to use an example under thermal conditions, and I'll note that the Woodward-Hoffmann rules require a total that is odd. And we'll see the consequences of that on some stereochemistry. I'm just going to use an example of a substituted hexatriene, and I'm just going to draw it at a sort of slightly side-on perspective. And I'm going to have substituents R1 and R2, and I'm going to start here with the EZE isomer. That will allow the two ends to reach, and I'm going to see what the consequences are when I do an electrocyclisation. Okay, applying the Woodward-Hoffmann rules, I identify my pi system first, which I can just do here in red. All that is a pi 6 component altogether. I can apply my Woodward-Hoffmann rules. I need to look for how many superfacial components I've got that are in the sequence 4q plus 2. I need to look for how many antirofacial ones I have that are 4r. And I have a total that I need to sum here. Now, this particular way of looking at this is quite simple. There's only one thing that can contribute to our sum. So therefore, the total must be 1. We have a pi 6 component. Now, that can only go in this 4q plus 2 sequence. So combining this together, we require that the pi 6 component is S. Now, once we've defined that, we can draw this on the picture. S means suprafacial, means coming out of the same side. Now, one way I can do that is just start on the left-hand side and come out of this top one in green here. And I can come out the top on the right-hand side as well and just join them up. So our ring closure will be to turn the end carbon on the left in a clockwise fashion and to turn the orbital on the right-hand side in the anti-clockwise fashion. So to form the bond under thermal conditions, we have to rotate these bonds in a disrotatory fashion. I'm just going to abbreviate that to dis, which is conventional. And we'll end up with this specific product, which has the shortened pi system, but the two R groups both on the same side. Now, this is, of course, racemic because we've not put any enantiomer control into this. And this is by far the easiest way to analyze but using the Woodward-Hoffmann rules. I'd strongly encourage you to look for the longest conjugated system and deal with a ring closure. But, you know, sometimes it's not that obvious, particularly if you have lots of different types of atoms in your system. Sometimes it's not that obvious to spot the conjugated system. So you can analyze this in different ways to also come to the same conclusion, which is reassuring that the maths behind Woodward-Hoffmann rules is robust. I'm just going to give myself 2 more systems to play with, just to show that we can get the same conclusion however we use the Woodward-Hoffmann rules to analyze. Okay, so that's just 2 more repeats of the same hexatriene that we had before. I can put my p orbitals onto them. And what I want to do now is just pretend that I haven't remembered that the system is conjugated. So I'm going to analyze this slightly differently. So rather than looking at one big continuous pi 6 system, I'm just going to identify the individual carbon-carbon double bonds and call each of them a pi 2 system. So it's all the electrons are being counted here. I've just got 3 components that are going to go into my Woodward-Hoffmann rules instead. I'm actually going to do the same on the right-hand side, and we'll see why in a second. Okay, the next step is to use the Woodward-Hoffmann rules. So I have 4q plus 2s, 4r, a, and I need my total here. Now I need my total to be an odd number under thermal conditions. So the only possible options I've got here for my 3 components are that the answer is 1 or 3. Doesn't actually matter which. We can have a look at my system, and actually all of these pi 2 components fall into this top category. So I have 3 of this type. And that's enough for us to make a conclusion on what must be happening. Therefore, we have to link up as either S, 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 so all the components being suprafacial, which will give me the total of 3, or equally validly, S, A, which will give me the total of 1. And I can just show these on my 2 pictures. So just taking this suprafacial example first, that's the structure with the green star. Well, it makes sense for me to find some overlaps that are suprafacial, so I can just arbitrarily start at the back. Now, it would make no sense for the electrons from this back orbital here to teleport to the other side of the ring. So overlapping them here is not particularly controversial. Those parts of those orbitals will always be overlapping in this type of reaction. We can also say the same on the right-hand side. That will define the back component as suprafacial, so pi 2s. Now the choice gets made. Well, okay, we've said everything should be s. So if I put s down the front on the left-hand side, that will make me come out of this top bit of the orbital here to be suprafacial for that component. Same goes for the right-hand side. If I make that suprafacial, I come out of the top. And then just joining them up in the middle, we come to exactly the same conclusion, that these orbitals will have to rotate in a disrotatory fashion. And again, that will just take us back to the same stereochemistry of product that we had before, which is reassuring. Now on the right-hand side, just a structure labeled with 2 green stars. Well, I can do the same treatment. The back one, again, we can define as suprafacial. That's non-negotiable that these orbitals have to overlap geometrically for this reaction. We can't have the electrons teleporting randomly to the other side of the molecule. Now what we're saying is the other two components are now forced to be A, so pi2A. Now what does pi2A mean on the left-hand side? Well, the pi2A means we come out of the bottom of this component, and again on the bottom of the other component. So to get the reaction to work, these two orbitals have to overlap. And actually, if we see what we have to do rotation-wise, well, to get that to work, I need to rotate anti-clockwise on the left-hand side, but clockwise on the right-hand side. Now that's still disrotatory, and it will still go to our product. So actually, there's no wrong way to do this. Each of these analyses are equally valid. They just take a bit more time to do. Okay, and in the spirit of seeing alternative ways of using the Woodward-Hoffmann rules, there's one final way we could analyze this, which admittedly is a bit contrived. But when you have lots of different atoms in there in a complex molecule, you might make this conclusion. So I'm just giving myself the same picture that I had before of the EZE hexatriene, same p orbitals. But this time I'm going to remember that I've got some of it conjugated, say this bit in yellow, and I've identified that as a pi4 system, but then I've forgotten that the other bit is also conjugated in. So I'm going to treat that as a separate pi2 system. In fact, I'm going to do the same on the right-hand side as well. So this is an example of using the Woodward-Hoffmann rules where you have two components to think about instead. We still have to worry about our 4q plus 2s components and our 4ra components. And again, if we're considering a thermally controlled system, the sum must be 1. It's the only odd number that we can get from two components. But the difference we have with this case is that the pi2 component belongs to the first category and the pi4 component belongs to the second. So we have one of each. But that's okay, the logic still works. That means that we have requirements on our labels that we require either they're both S, so that means the pi2s component will get counted, but the pi4s won't, or we use both of them as the A components. That means the pi4a component will be counted and the pi2a will not. Now I will stress again that both of these approaches are valid. Okay, I'm going to label the first example here with an orange star, and going back to the left-hand structure here with the orange star, we'll be defining both of them as S. So that's S and S. Well, we can join these two components together at the back. Well, a geometrically sensible thing to do here would be to join these ones up. The electrons aren't going to teleport from one side of the molecule to the other there, as before. And now to define the left-hand side, the pi4s component, the orbital lobe that we must use is the one on the top. That makes it a pi4s component. And on the right-hand side, we've got to come out the top as well. That makes it a pi2s component. Joining them up as usual, that means that the left-hand side with R1 has to rotate in a clockwise fashion, and the one with R2 has to rotate in an anti-clockwise fashion. We get exactly the same thing. We get the disrotatory formation of the same product we had at the top. Just to have a look at what happens when we define them both as antirofacial. So the structure of two orange stars. Again, I'm going to join up the bits at the back because that's geometrically sensible. I have them defined both as A in a thermal cyclisation. To define that pi4 component as A, I have to come out of the bottom. And to define the pi2 as A, I need to come out of the lower part there as well. Join those two bits together. That means that the group with the R1 has to rotate anti-clockwise and the group with the R2 has to rotate clockwise. That will take me also back to the same product as before. That's a disrotatory process. Now, this is always going to be the analysis that you do with electrocyclisations. I should stress at this point that there is a big difference between electrocyclisations and cycloadditions, for example. Every single electrocyclisation is allowed, whether you use photochemical or thermal conditions, just changes whether the process is disrotatory or conrotatory, and that will usually have an impact on the stereochemistry of the product that you form. So at no point should we be worrying whether an electrocyclisation is allowed or not. They are always allowed. Now that's an awful lot of trienes. Perhaps we can just see how this works on the diene as well. So I'm just going to give myself a little box down here. I'm just going to consider the arrows that we had right at the start of this video for a butadiene. Just going to put some R1s and R2s on it as well, just to keep track. So here I've got the EE geometry, and the arrows I'm going to try and represent are these ones. Now, just with a side-on perspective, I would have something like this. And I can just do the analysis as I did it before. I'm going to put my p orbitals in. Now I could break this into two separate pi2 systems, or I could just do it the easy way and consider it as one continuous conjugated system. That will give me one Woodward-Hoffmann component that's pi4. Now I'm going to define the conditions I'm looking at as thermal. That means I need my total to be 1. Therefore, I need a pi4a component because there's only one component I can assign a label to. So my system is going to cyclize in an antiraphasial manner. That means I come out of the top of one side, say on the left-hand side here, coming out of the top near the R1. And I'm going to use the lobe on the opposite side to make it antiraphasial. So that means now when I want to join these up, I'm going to have to rotate in this sort of way, which means my R1 is going to have to rotate in a clockwise manner like this. And my R2 is also going to have to rotate in a clockwise manner. So this is a conrotatory process. And my product will be this cyclobutene, but specifically with the R1 and the R2 groups anti to each other. And of course, this will be racemic because I haven't used any enantiomer control here. Now, I said at the start of this video that it's important to note that these reactions are all reversible, and that's really helpful for us. That means that whenever we do an analysis of an electrocyclisation, whether it's a ring closing reaction or a ring opening reaction, we could always just do the Woodward-Hoffmann analysis on the ring closure like I've done here. If you can prove whether the reaction is disrotatory or conrotatory in one way, it must be the same in the other. So I would always just say, oh, I'm going to consider the ring closing process whenever I'm looking at this type of reaction. But the Woodward-Hoffmann rules do allow you to do ring opening if you really want to. They're just not as simple as using one pi system. It's perhaps just less intuitive than what we've done here already. But for completeness, I'll show you how to do it. So if we've proved the cyclisation mode for ring closing, it must always be the same for ring opening. Let's just have a look at an example. Let's take the product we had before. That's this cyclic diene, R1 and R2. I want to analyze the ring opening, which is the arrows that look like this. Now I'm also going to take the side-on perspective as I did before, particularly to emphasize the sigma bond that's going to break. And I've got my R1 and my R2 pointing up. Now I need to put my orbitals in. So I've got my pi orbitals like I had before at the back, they're just in red. And I'm going to draw my sigma bond at the front in orange. So the sigma bond, of course, has the larger components of the orbitals in the middle there. Okay, so the sigma component is a sigma 2. The pi component, well, it's all conjugated, so I'm going to treat it as one whole system. I could treat it as two pi systems if I wanted to. I'm just giving myself unnecessary extra work there. I do my Woodward-Hoffmann analysis, 4Q plus 2S, 4RA. Now we've got the same situation as we had before. I'm going to define the reaction as thermal. I need an odd number to come out of my sum. And if I've got two components, the only possible number that I can get out of this is a 1. And I've got one of each type again. So we can go straight to a conclusion as before. We have SS or AA, and it doesn't matter which, so I'm just going to draw out both of them just to see. I'm just giving myself a copy of the picture there. Okay, so the SS one, we can just draw over here. Now, if we make this pi4S and pi2S, well, we need to define what we mean by suprafacial for a sigma bond. And what we normally do is we say that it's the same two sides. So the orbitals in the sigma bond are made up of a large bit and a small bit. So suprafacial, we mean the same bit. So we either use two big bits or two little bits. Doesn't matter which, we'll get the same result. So to make the pi4S component, I'm going to come out of the top face on both ends of the pi system. So that's out of here and out of here in green. Now I need it to be S for the pi2 bits. Well, I'm just going to go into the middle here. So I'm going to use both the large components of the sigma bond. And then when I join those up, I get my conclusion. So for the ring opening, for the breaking of this sigma bond, the R1 group is going to have to rotate anti-clockwise, and the R2 group is going to have to rotate clockwise. So as we see again, we get a disrotatory ring opening, and we'll get the same geometry as triene product as we had at the start, which is EZE. Now for the AA version, I'm just going to draw in purple. So I need a pi4A component. Well, that's going to be coming out of, well, one side on the left-hand side, let's come out of the top, and let's come out of the bottom end of that pi system on the right-hand side. That's defining that as a pi4A component. And I need to come into the opposite ends of the sigma bond as well. So one of those needs to connect to one of the big lobes and one to one of the small lobes. So let's just pick one possible option. Anything's geometrically sensible here, so it's all okay. I'm going to take one big lobe and one small lobe. Joining up the big lobes on the left-hand side, that means my R1 will have to rotate anti-clockwise. And joining up the lobes on the right-hand side, that means the R2 is going to have to rotate clockwise. So we get exactly the same conclusion, that this is a disrotatory mode of ring opening, and we'll go to the EZE triene as well. So that discussion's been a bit theory heavy, and I thought I'd just finish off showing you how you could use this in a retrosynthesis of a natural product. And specifically, I'm going to use the Nicolaou synthesis from 1982 in a synthesis of Endiandric acid A. This is an absolute classic for this topic. So we have quite a complicated natural product structure, which looks like this. Now this has this quite complicated cage-like structure and lots of stereochemistry, but we can use pericyclic reactions to assemble the whole lot. Now, just to make the synthesis a bit more easy, I don't really want to carry around that carboxylic acid in the bottom right-hand side. So in fact, the synthesis was done on the methyl ester. We can always hydrolyze that at the end to make the natural product. It will just make handling things a lot easier. So for a retrosynthesis, we've got 2 cyclohexenes. Now, a really easy way of making a cyclohexene is using the Diels-Alder reaction. So that's a pericyclic cycloaddition. Just having a look at this one first. Well, if I did a retrosynthesis on this one and move my arrows like this, well, I'm not really simplifying my life. I'm just making a really big ring there. And that in itself is complicated to synthesize. So I'm not super happy. That one is not a particularly sensible disconnection. We should aim to try and make things simpler as we go along. So the better disconnection is to use the other cyclohexene, the one here on the left. So I'm going to disconnect that using a 4+2 cycloaddition. Please see my other video for details, and do a Diels-Alder reaction. That will give me this diene, which we can see is perfectly placed to do a Diels-Alder here. Now, one thing we can also see about the stereochemistry here is that that diene is all held below the plane of the paper, and the 6,4 ring system is sort of curled round, so the 4-membered ring is curling down into the plane of the paper. Just to check that the stereochemistry all works, we can draw this in 3D. So this is the 6,4 ring system. I have my hydrogens going up. This methyl ester is just out the way. But that hydrogen is on the same face as the ester. So therefore, when we're lining up the diene for the Diels-Alder reaction, we can see that this is indeed what we need. We've actually got an exo transition state here. We often call this a tethered reaction, where the diene is tethered to the dienophile. The system is all forced by an intramolecular reaction instead. In any case, when we form those 2 new carbon-carbon bonds formed in green, these 2 hydrogens in orange will be forced down. And that's the stereochemistry that we need in the product. Just having a look at the natural product again at the start, that's these 2 hydrogens here that I'm just highlighting in orange. Okay, so we've made a bit of progress there using a cycloaddition disconnection. The next step is to identify what pattern we have here. Well, we have a cyclic diene. And that's a pattern for electrocyclisations. So I can do another disconnection on that 6-membered ring, which will look something like this, to convert that ring into a triene. Okay, so the left-hand side of the molecule is staying as it was. And that gives me this product here. So that triene is actually trapped inside an 8-membered ring here. Now I've actually drawn the geometry that we'll get from this electrocyclisation, but just to convince us that we've got the right one here, we're forming the EZE geometry. And that's come from a 6-electron electrocyclic reaction. So drawing this a little bit like what I did earlier on in the video, well, we can see what we need if we keep track of the hydrogens. So we've got a hydrogen on the inside here and a hydrogen on the inside here, and I can draw them on my actual structure. I need both those hydrogens to go up. So therefore we need thermal conditions for the electrocyclisation, because in that sort of set of conditions, you'll reversibly go both up or both down. Now, actually, it doesn't matter whether in the forward reaction, we get both up or both down, because only the one when they're both up will the Diels-Alder reaction be able to progress forwards. Otherwise, the Diels-Alder reaction won't be able to occur because the cage won't be able to form itself. The diene won't be able to find the dienophile in the Diels-Alder reaction. Moving on, we can use another electrocyclic reaction like this. This would be an 8-electron electrocyclic this time. So you need to keep a track of the numbers using Woodward-Hoffmann rules. As an exercise to yourself, you can show that if you do this under thermal conditions, we will get a conrotatory mode of reaction, which will leave us with the EZZE geometry of product, which looks something like this. Now, this is a particularly neat disconnection. We've now got a linear precursor And all we have to do is worry about the double bond geometries in here. Now, there's a standard way of dealing with the ZZ alkenes here, and that would be to do some sort of Lindlar reduction. This is a partial reduction of an alkyne using a poisoned catalyst and hydrogen gas. And that will take us back to this key, much simpler molecule, only containing double bonds that are reasonably easy to assemble. For example, this double bond here on the right, they found the best way was to use a sulfoxide elimination to make this. You can form these diene systems using a Glaser coupling, but you might want to have a look at the Nicolaou synthesis itself for the details of this bit. I wanted to just focus on the pericyclic components of this. So actually, in summary, all we need to do here is to treat this intermediate with hydrogen gas and a Lindlar catalyst, and then just heat it. And we'll go straight to this cage product. Now that's forming 8 new stereocenters, and it's a pretty impressive feat in natural product synthesis. If you enjoyed this discussion, please do give it a like and consider sharing and subscribing to my channel. I have some more retrosynthesis videos just on the way, but on the screen now are just a few others from my channel that might be of interest at the moment.